Today we're going to spend a little bit of time talking about higher order derivatives. So a higher order derivative just means that we're going to take the derivative of a derivative. We've talked about the first derivative pretty extensively at this point in time, and we know the first derivative is going to give us the velocity, how fast something is moving. The second derivative, however, is going to give us the derivative of the derivative, or we're going to call that the acceleration. And our third derivative is going to be the derivative of the derivative of the derivative, or the derivative of the second derivative, and we call that the jerk. Don't be a jerk about it, just the jerk. So a couple of things that we want to look at for notation-wise are velocity. We're going to see that as v of t. Our second derivative, acceleration, we're going to see denoted as a of t. Third derivative, we're not going to use it a whole lot. Really, we just do it to kind of have fun with it and do it at this point in time. So there's really no application to it at this point. They are looking into things that could use a third derivative, but at this point in time, we just call it the jerk and we go on with life. You could find the sixth derivative, eighth derivative, 20th derivative if you want. Really no necessary need for it at this point in time. So again, some notation. First derivative, we have f prime of x, or dy dx. The second derivative, we denote it as f double prime of x, or d squared y over dx squared. So it's the second derivative of y with respect to x. So notice that notation, we square the first d in the numerator, we square the x in the denominator, so second derivative of y with respect to x. Third derivative, we do d to the third y over dx to the third. We can also put an f and a little 3 in parentheses. So normally when we get above 3, we start using this notation. So we do f maybe to the sixth power in parentheses as the sixth derivative of a function. So how do we go ahead and find the higher order derivatives or a higher powered derivative? So if we want to find the second derivative of f of x, we have 3x to the fifth plus 2x to the third minus 6. First derivative, or the first thing we're going to do is find the first derivative. So we're going to find that. We have a nice power rule here, so we have 15x to the fourth plus 6x squared. And then our second derivative, f double prime of x, is going to give us 15 times 4 gives us 60, x to the third plus 12x. I guess I want to go back up also and talk about that notation. Remember, first derivative, we're doing maybe meters per second for our units. Second derivative would be meters per second or meters per second squared, which you've probably talked about in your physics course a little bit, but we'll touch on that as well as we get into some of our problems. So first derivative is meters per second, second derivative meters per second squared. All right, moving on here. We're taking the second derivative of 2 secant of x. We're going to find the second derivative of that. So first derivative, not too bad. First derivative, we have 2. Derivative of secant of x is going to be secant of x tangent of x. Oh my goodness. Second derivative. Notice we have secant of x times the tangent of x. So to find our second derivative, f double prime of x, we're going to have to use the product rule. Product rule, remember, is 1d2 plus 2d1. So there's our first derivative of tangent. Derivative of tangent, hopefully, remember, is secant squared of x. And to that, we're going to add the second, 2d1, so tangent, and then derivatives of 2 secants of x. Derivative of 2 secant of x, we had that up there, is 2 secant of x tangent of x. We can go ahead and clean this up just a little bit. Not a whole lot we're going to do with it. So we have 2 secant to the thirds x plus 2 secant of x tangent squared of x. And that's pretty much all we're going to be able to do with that. Down here, example 3, we're given f third of x, or the third derivative of x, as being 4x to the fourth plus 5x squared minus 3. They want us to find the fifth derivative of x. So you got to be careful with our notation because they're already giving us the third derivative. We don't need to find the fifth derivative of the, or find the derivative 5 times. We just got to find the fifth derivative. So in order to find the fifth derivative, well, we can go ahead and find the fourth derivative of x. The fourth derivative of x is going to be 16x to the third plus 10x. And then our fifth derivative of x, we're going to have 48x squared plus 10. And that's all we got to do. So be careful with our notation as we get into some of our problems. And we're going to end the day with a nice little word problem. Here we're given the position of an object. It can be found by using s of t equals negative 16t squared plus 1296, 1296. Determine the velocity and acceleration of the object when it first strikes the ground. I guess we should probably put some units on this. I guess I didn't put any units in there. Let's say s of t is giving us in feet. In feet, we'll need that. And our time is going to be in seconds. We'll go ahead and put that notation in there. Probably should have done that as well. All right, so we want to find the velocity and acceleration. We're given a position. Notice our symbolization, s of t. S of t normally denotes we have position. So to find the velocity, v of t, that's going to be the first derivative of the position, s prime of t. Well, that gives us negative 32t. Our acceleration is the first derivative of velocity, or the second derivative of the position. Not that you have to write this notation down, I just want to kind of get it into your mind of what we're looking at and how it's all going to come together in the end. So acceleration is the first derivative of velocity, the second derivative of position. Velocity is the first derivative of position. So here we get negative 32 as our derivative. And we can go ahead and put our units on here if you want. This is going to be feet per second, and this is going to be feet per second squared. All right, so when is this thing going to first strike the ground? How can I figure out when it's going to strike the ground? So I can go ahead and find when it's going to strike the ground because I know the position or the height of it is going to be 0 when it strikes the ground at first. So we get negative 16t squared plus 1296. We can go ahead and throw it into the calculator. Solving for that, we should get, let's see, 1296 divided by our 16. We get 81. Thought it worked out nice and clean for us. So 81 equals t squared, so 9 is going to equal t. So this object is going to strike the ground after 9 seconds. So our velocity at 9 seconds is going to be negative 32 times 9, which gives us negative 288 feet per second. And our acceleration, a of 9, is going to give us negative 32, since there's no variable there, just negative 32 feet per second squared. Now we could take this a step farther. If you recall from the previous section that we were talking about, we talked about speed. If I ask you, can we find the speed of this object when it first strikes the ground? If you remember, speed is the absolute value of velocity. So the speed at which it's going to go is going to be 288 feet per second of this object. And that would give us, again, something else that we could do with this problem if we chose to. And that kind of gives you an idea of our higher order derivatives and an application of where we would see higher order derivatives. Good luck.